this is Thevenin's theorem. And this down here in the corner is a young Thevenin, who was a technician, I believe, for the railroads in Europe, when he realized there was a better method for analyzing circuits that have two sources. So we'll use this one as an example. See, it has a 24-volt circuit source and a 72-volt source. Now, you can pick anywhere to analyze. We're going to pick the 12 kilo ohm resistor, just for the example. What you do next is to pull out the spot that you've decided to pick and take a look at, and you're left with the rest of this circuit. Now, the analysis is going to be a little bit tricky and a little bit difficult, probably time-consuming, but the power of Thevenin's theorem is that the 12 kilo ohm then is very flexible. You could then very easily make it 3, 4, 5 kilo ohms, 1,000 kilo ohms, whatever, and not have to redo the math like you would in other methods of analysis. So you take out the 12, like so, and you replace it with two nodes, and we can call it respectively A and B if you'd like, where they were both attached. And we're going to turn the rest of that circuit that you see into one single voltage Thevenin and one single resistance Thevenin. Okay, right here is the resistance Thevenin. Now we just use Thev as a subscript to identify it, but you'll take a two-source circuit and turn it into a single source circuit. And however many resistors you have, in this case we have 2 extra left over, the 4 and the 6 kilo ohm, and we'll turn it into a singular resistance Thevenin. Let's start with the analysis for resistance Thevenin because it's probably the easiest. In doing so, the first thing you have to do is get rid of the sources. When you have voltage sources, what you go ahead and do is short them, which means place a wire over them. And since current flows to the point of least resistance, it's going to flow through those empty wires before it goes through the sources. If you had current sources, you would then open them up. But for now, we're going to short these because these are voltages. You then go ahead and you place in an ohm meter. And an ohm meter has its own and its own current. So you can almost treat it as if it's its own source, if you'd like. So what you're going to do is you're going to take a look at the same point A and point B, and you take a look at what you actually have is a circuit, right? The 4 kilo ohm is attached to the A over here. And if you go through the naked wire over here, it's attached to the B. And this 6 kilo ohm is attached to the A and attached to the B. Now, more simply, if you'd really like, you could turn the ohm meter into a little source. And what you would actually get, since they're both touching points A and B, would actually be something that looks like this. This is your 4 and your 6. And if you notice, this is a more traditional way of looking at a parallel circuit. So 4 and 6 kilo ohm resistors are in parallel, which means that we will use the product over sum method to find a equivalent resistance. That means a 4 times 6, all divided by 4 plus 6, giving us 2.4 kilo ohms for our Thev. Now we're going to hold on to this information and bring it back later. Now we're going to go to slightly more trickier, which is finding out the V Thev. So the voltage here, we will have to do a loop. Now what you would do is you would start from ground, because ground is your 0 point, right? And what you'll do is assume clockwise, much like you would have done in mesh, and you would polarize the resistors, which are not polarized until you make this an assumption, this way, because you are going positive to negative in a clockwise motion. So to find the I Thev, we're going to start at the ground. So here, this 0 is ground. And then the next step for the 24 volts would be going this way over the 24 volts. If you notice, you go from negative to positive. So it is a positive 24 volts. Your next step is to then go over the 4 kilo ohm resistor. And you'll notice it goes from positive towards a negative. Now, what we're doing is solving for voltages. So even though this says I Thev, it's because the unknown when you do a loop is I, and that's what we're solving for. So what happens if you're going to use a Ver method to find, so a voltage is equal to the IR. So there is your unknown I, and there is your R. So you're going to take voltage, right, times 4, so it's 4 kilo ohms, times an unknown I, And since you're going for positive and negative, it is a minus value. You're going to do, again, the same for the 6. So it'll be minus 6 times I. And then if you notice when you hit 72, you go from plus to the minus end. So it is a minus 72. This gives us a negative 4.8 milliamps. Now, some people don't particularly like this. This method of starting at ground and starting at 0 is one way. Sometimes I'll just bring the 0 over here because I like to have a number on the other side of my loop equation rather than solving for, but that's just a matter of taste. What you'll notice, though, is that what you end up getting for current is a negative milliamps. Well, that would mean that our assumption of clockwise was incorrect. So what we now have to do is actually assume correctly, which is counterclockwise. So if you'll notice, we go ahead and do the loop back in again, but this time the resistors are polarized positive, negative, if you see, in the opposite direction, so we can follow along with the assumption of counterclockwise. So now we're going to go ahead and put in a voltmeter. Okay, and what you do is you have a voltmeter. Now, voltmeters have what they say, infinite resistance. That means nothing's going to go through there. So you're really measuring the voltage at point A and point B. Okay, so we're going to go ahead and solve now for a VThev. Now, again, I like to start at ground. If you start at ground, this is your, right here, this is your ground. Okay? And it is 0. Now, if you like the 0 on the other side, that's fine. But if you go to ground, and if you come this way, now you'll notice you go from negative to positive, so it's a positive 72. And then you'll go all over to the 6 kilo ohm, and if you notice, you're going from positive to negative. So it's negative 6 kilo ohms. And if you recognize this now, since we're going in the direction of current, it is a positive 4.8 milliamps. This is what we got for our I, Thev. Okay? That then gets us 43.2 volts, going from point A to, or actually from point B to point A, respectively, since we're going in that order. Now, you could also do it the other way, meaning we could go ahead and go from B to A the other direction against current, which, you know, is a method. And you'll see that if you go the other way, you'll get 24, okay? Right, if you go from B to A this way, you'll get a positive 24, but a little bit differently now over this resistor, since you're used to dropping all the time. You're not dropping because you're going from negative to positive, and you'll see that this is a positive 4 kilo ohms times the I Thev of 4.8 ohms, which also gives you 43.2. I like to follow the direction of the current because I find it less confusing. And in the case of the resistor, I ended up dropping, which is what I'm used to doing in general for resistors. Now, let's put it all together. You received a 43.2 volt VThev, and you've received a 2.4 kilo ohm RThev. So now we took it, put it back together again. Now we're going to put back the 12 kilo ohm resistor that we removed at the beginning. And now, if you notice, it goes in one after another. So it's not that they have shared nodes, they are now in series. So the R total is 2.4 kilo ohms, which is your RThev, plus the one that you're analyzing, which is your 12 kilo ohms, giving you 14.4 kilo ohms. Now, using Ohm's law to solve for current, you use 43.2 ohms over a total of 14.4 kilo ohms, which is 3 milliamps. Now, to find the voltage that is dissipated by just the 12 kilo ohm resistor, since that's what we were analyzing, you will take the 12 kilo ohm resistor, right? You'll invert it again, and you'll end up getting 3 milliamps, which is what you found in the previous one, which is how much current we have in this circuit. And now you have 36 volts. Now, the amazing thing about this, though, is that now, if you really want to change this, now you've done all this work, is that very easily I can go ahead and change this. I could change it to, let's say, 10 kilo ohms. Let's say I just want to change it, okay? That would then change this to 10 kilo ohms, right? And this would be what, 12.4 kiloohms. So you can go ahead and change some of this thing. That would make an alteration to this amperage, which you would have to change there. Okay, and then you could change this guy to 10, and then you would get another value. Okay, and I could go ahead and replace out this 12 kiloohm resistor with whatever I want. I could do this a million times infinitely, but I don't have to go back and change because the rest of the circuit is still going to have this VThev and this RThev, which makes this very flexible. Now, if you don't believe me, I used multi-sim to check it. If you notice, what did we get for we said 36? Well, 35.993. That's pretty good. So this is the original circuit. When you do this measure, this is your point A, and the grounds are the same spot. So that means ground and ground are both equal B's. Well, so what are you getting a measure of? Well, clearly 35.993 is as good as 36 volts, right? Now, if you use a Thevenin equivalent, which if you notice, this is your VThev, and this is your RThev, okay? And you put in your 12 kiloohm, and you're measuring a voltage. Remember, the voltage is the same over parallel, so you go ahead and measure over, and you get 36. Well, they're both 36. So whether you use the original circuit in your checker like multisim, or use a Thevenin equivalent circuit, they end up being the same. That is impressive. And Thevenin was right. So again, a little tricky because you have to do loop equations, but very powerful and very flexible. All right, hope this helped you out learning a little bit of Thevenin analysis on a circuit with two sources. Bye.